So in this video, we're going to look at applying the difference quotient when we're working with a rational function or a function that is a ratio of two polynomials. So here it says use the difference quotient to find the slope of every arbitrary secant line associated with the function f of x equals x plus 1 over x. In this case, we're not being asked to find a specific slope for a specific secant line because the idea here is more to get practice applying the difference quotient to a rational function, which we'll need to do in subsequent homework assignments. So to establish a formula for the slope of the secant lines for the function f of x, we're going to use the difference quotient. So it's going to be f of x plus h minus f of x all over h. And with rational functions, it's going to look a little bit more complicated, and that's why we're doing an example. So the first step is take your function f of x, and everywhere you see an x in both the numerator and the denominator, replace that x with x plus h. So in the numerator, I'm going to get an x plus h plus the 1, replacing this x with an x plus h, over, now I have to replace the x in the denominator with an x plus h, minus the original function, which is just x plus 1 over x. And then it's all over, so this part here is just this difference in the numerator, and then it's all over an h. And then probably to make my life easier, what I want to do is factor off a 1 over h, so that h is in the denominator position, and then I'm going to deal with the numerator stuff over here separately. So when we have a difference between two ratios, we want to find a common denominator. So my common denominator is going to be x times x plus h. So I need to multiply this guy here by x over x, and this guy here by x plus h over x plus h to get my common denominator. So I'm going to have x times x plus h plus 1, x plus h plus 1, minus x plus 1 times x plus h. And use of parentheses here is vital for not making mistakes. So this is all going to be over my common denominator, which is x times x plus h. And then what we want to notice is that this h will tuck nicely into the denominator position for us. So equals. First, I'm going to simplify this numerator, so I'm going to distribute the x into this parentheses. I get x times x, excuse me, x squared. X times h is plus xh. X times plus 1 is plus 1x. Minus, multiply these two terms out. So parentheses, x times x, x squared. X times h is plus xh. 1 times x is plus 1x. Plus 1 times plus h is plus 1h. And this is all over. My denominator now has h times x plus h. And now I can distribute this minus into the parentheses. So I get x squared plus xh plus x minus x squared. Minus plus is minus xh. Make that squared look a little bit better. Minus plus x is minus x, and minus plus h is minus h. And this is all over the denominator h times x plus h. And then if I look at the numerator, some things are going to cancel, or they're going to give me a 0. So I get x squared minus x squared is 0, plus x minus x is a 0, and plus xh minus xh is a 0. So when I look at the numerator terms, the only thing left is a minus h. So I'm going to step over here, so I get m secant. The slope of the secant line is equal to, I have a negative or opposite of h in the numerator, over my denominator, which is h times x, times parentheses x plus h. And then I want to notice that h divided by h equals 1 as long as h is not 0. So this is going to simplify to negative 1 over x times x plus h. So there is the slope of all possible secant lines associated with the function f of x equals x plus 1 over x.